Hey, I'm Adam Wagner, and this is the magnetic field of a bar magnet lab. The purpose was to evaluate how distance relates to the electric field on axis of a bar magnet through procedures and calculations. Some physics principles that we used were the equation for the magnitude of the electric field from the bar magnet, and on the right is the expression for the distance dependence of the magnitude of the electric field. And then some systems that the system that we define is the bar magnet and the magnometer, while the surroundings is Earth's magnetic field and everything else that surrounds it. A little preview to our results. We're going to find that the magnitude of the electric field from the bar magnet drops off at a rate of 1 over r cubed when on axis. Our procedure for this lab was first we aligned our phone with magnetic north, so where the x value is equal to 0. Then we found the location of the magnometer on our phone, and then we found the distance where the magnet caused the magnometer to have certain values of magnitude 20, 70, and 120 microteslas, going up to 220. Then we graphed our data using the Excel sheet provided. Then we calculated the magnitude of the magnetic moment of our bar magnet. Then we did a similar procedure for for an angle of 45 degrees. Here's my model for the electric field of a bar magnet. As you can see, the on-axis observation points are about twice as big and in the opposite direction of the perpendicular observation points. And you can also see the 45-degree angle up in the top right, which is the purple arrow. Here's part 1 of my data. In the first part, we found various distances where the electric field were at different values, such as 20, 70, 120, 170, and 220. And then at the bottom, you can find our data for our off-axis field, where we found distance perpendicular, and then eventually we calculated the net magnetic field at that point. Here's a graph of our data. We use this Ln equation to linearize our graph to find the n and the k values. Our n value ended up being 2.849, which is very close to the expected value of 3. Then we use this equation to find the magnitude of the magnetic moment of our magnet, which ended up being 3.145 amps meter squared. Here's the first part of my code. First we have our magnitude of the magnetic moment, and then at the bottom we have a function for the magnetic field. Here's the second part of this code. Basically just makes all of the arrows that you saw on our model earlier in the slides. Here's the last part of my code. It creates the 45-degree off-axis arrow in our model. Some important questions that we asked ourselves are, what if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? This really would have just rotated our reference frame some angle theta, and we'd have to add vectors at this point instead of just the magnitudes of the magnetic field. And it would just make our calculations and data much more elaborate. Second, what if you were to stick two identical magnets together end to end and run the experiment back? How do you expect your measurements to differ? This would just double the magnitude of the magnetic moment of our magnet,